Okay, thank you very much for joining. This is the webinar for generative models and deep learning. So we'll take around 45 minutes to an hour to go through this topic, very basics and intro level starting information. At this point of time, that's what potentially webinars could do, a short webinars. A little brief about who we are. I'm Raju, I'm part of the Big Data Trunk team. We are a professional training services company established in 2008. We provide online and in-person trainings, mostly to corporates, but we have few public trainings for individuals. Large focus on technology, mainly data, AI, and those stuff, as you can see, but cutting edge technology, but we also provide soft skills, leadership, boot camps, upskilling, a lot of that focus from the corporate side, but also individuals to a certain degree. We have a lot of different courses. Today's topic is very relevant to generative AI. In that area, we have a lot of generative AI courses. We have e-learning things as well. I'll share some of the free resources and things which we have a little later as we progress in the topic. That's what we are planning to do for the generative related things. Today's topic is generative models and deep learning. The speaker for today's topic is Kiran. Kiran is part of our team, one of the instructors. She's very focused on the generative AI space. It's cutting edge, and I think there's a lot evolving, so always excited to present and bring new things. It's always a lot of research is needed, so we're trying to bring our 2 cents and share with the group. So hope you'll find it interesting, and you can feel free to submit next topic interest or some things you'll have in the chat as well. I'm monitoring the chat, so if you have any questions, put in the chat. As said, we'll record this session. We are recording this session and we'll be posting it. You'll have access to that on our YouTube channel. And we'll open up for Q&A in the very, very end. So with that, I'll stop share and welcome Kiran to really take over. Over to you, Kiran.
Thank you so much, Raju. That was a brief introduction about today's topic and everything, so I'd not like to go there. Hello, everyone. Welcome to the webinar. Today, we are focusing on generative AI models and what is deep learning and the connection between that. So without any further ado, let's get started directly. So, artificial intelligence. Now, imagine you have a friend who's a great artist. You can ask this friend to draw anything or compose a music, create scenarios, or generate poems and essays, and they can create it for you. Like they can do any sort of homework you're given, be it in your art school or be it in your mathematics class or anything. Now, since that friend is a great artist, he has the potential or the skill of creativity. What if a computer could be like this, right? That is what generative AI models do. They can do image creation, they can do new recipes, they can do healthcare, create music, and a lot more. What do is they learn from lots of examples and then they create new things that are similar but not exactly the same. For example, if we show in generative AI lots of pictures of dogs, it can learn to draw new pictures of dogs that it has never seen before. And it can also distinguish between like a tested model. So if it is a dog or a cat or a donkey or anything. Why? Because we have trained it. Now, generative models in layman language are a fascinating area of technology. They combine both creativity and computing. But then, in the field of machine learning, generative models are a class of statistical models. They try to understand how their data is distributed in the training set so that they can generate their own data points with some variations. These models come under the unsupervised method category, and they generate new data which resemble the training set that we have provided for them. Generative models, there are a lot of examples. We have generative adversarial networks, we have autoencoders, we have Gaussian mixture models. All of these are widely used for many tasks. Some of them are image synthesis and semantic image editing, style transfer. We have something called as neural style transfer, and it's like literally booming nowadays. We can try free resources as well. Then we have data augmentation and a lot more. Usually, like whenever we think about AI, what is the first thing we get into our minds? ChatGPT, right? Or DALI or anything. In the context of OpenAI, like we have that particular company has developed a lot of big range of generative model, and each has its unique capabilities and applications. Now, some of the most well-known models developed by them, we know are GPT-3 for texting, DALI for the images, and Whisper for speech recognition as well. So imagine how fast-paced it's going right now. Let us understand, before going inside and understanding deep what generative models are, let us understand the timeline of generative models. Now, uh, okay, there's something called as discriminative as well. I'd like to first go there. Now, there are two types. We have generative and we have discriminative. What are generative models? They learn to create data. Generative models actually learn the patterns in the data and they can create new similar ones. While the discriminative models, complete part in statistics, they focus on learning the boundary between the different classes and they help to decide which category an input belongs to. Let us understand all of this in a brief. We don't need to go much inside. Usually, some of the use cases we identify between generative and discriminative would be generative can create new images, it can write new sentences, it can make new music, it can create things. While as discriminative models, they identify spam mails and they are here for face recognitions and they can give us customer reviews classification as positive or negative. And some common like model examples they use are VAs, autoencoders, which I just spoke about, and then generative adversarial networks. We are going to see this in much details later on. And something called as logistic regression, support vector machine, deep neural networks. All of these are a part of statistics and deep learning and machine learning. Now, what do generative models do? The training focus of them is understanding the whole picture. They understand both the inputs and outputs, which means they can generate new examples that look like the training data. And discriminative models focus on differences. They only care about how to distinguish one thing from another, not to create examples. We can take an example task like the art creation, like a robot can create paintings and it can create new pictures. Whereas a discriminative model can actually do the spam detection. It can detect your emails and filter the spam for you. So that's what it is. Now the timeline of generative models. This journey actually was a very fascinating tale of progress and innovation as well, because we started way earlier in the 1940s and 50s. That is where people started to think about how to make machines smart like humans. Then in the 1960s, we started teaching the machines to learn from their experiences. After that, in the 1970s, after we're moving forward, something called as neural networks came ahead, making the machine models actually work like the human brain. Next up, we made a big leap in how machines learn from their mistakes. That was in 1980s. In 1990s, we created models that can remember past information to make future predictions. That is the LSTM models. 2000 were there for the generative adversarial networks. This is a type of model that can create new data similar to what we have already seen before. And then in the 2010s, we have something called as transformer models. They are a type of improved models that can understand the machine language completely differently. Now, after understanding all of them, we came into the present by creating a completely different advanced models like GPT-3, DALI, Whisper, Runway ML, GAN Labs, and a lot many variations of AI. Like we can see thousands and lakhs of AI variations already. Now, this is the timeline of generative AI. Usually, these advancements that are happening are actually blurring the line between human and machine creativity. And while they're opening up very new possibilities, we still need to be careful because we are getting a lot of, social consciousness that, yeah, this is something new to us. Even though it's very fascinating, this is something new to us. And we need to be very careful on where it turns out. So AI is both a very good thing and a very bad thing as well if it gets out of hand. Now, let us understand the types of generative models. We have the main two types called as variational autoencoders, that is the VAEs, and the generative adversarial networks, that is GANs. Usually what happens is, the differences lie like this. Variational autoencoders, they focus on learning in a smooth latent space representation. I will be telling you what is latent space in later classes, like in the later period. Then, and they typically produce slightly blurry images due to the Gaussian assumptions we have in the latent space. We need to give a proper assumption value to them. And the more near they are to the assumption, the more better you're getting your images. And these VAs are easier to train because they have a stable training process. And usually what they do is they encode the data into that latent space we are talking about, and they decode it back. What this does is it enables generation of new data points. I hope I'm understandable and the pace is also going good. Anybody's got any doubts?
All good, Kiran. I think the pace, I mean, I don't know, there is a lag, not lag, but the internet sometimes it catches. So a little slow would be great. But everything is visible. And thank you.
Okay. Yeah. Thank you, guys. Any doubts, you can put it in the chat as well. I'm looking at the chat also. Now, what do VAs do are, they are designed to generate new data points, just like any generative model. They have to create new data points, which are similar to the training data we provide. This is what we have been learning till now, right? So what they do is they achieve all this by doing the encoding decoding part. So between the encoder and decoder, there's something called as the latent space. Now, while this training process is happening, there are some like steps in the process. Like one thing is the loss function. What is the loss function doing? It combines the reconstruction loss. It sees how well the decoded data, which the autoencoders have created, matches the original data. So as soon as the data comes in, the data gets decoded first, and then it gets encoded, and then it's getting read. Now it has to see what the decoded data is and how it is matching nicely with the original data we have provided. And it calculates a proper loss between like both the differences. That's what happens. And then we have something called as back propagation. Whenever we get a particular loss, there it has to be decreased. The more you decrease the loss, the better you're getting your results. So to minimize the loss function, or to minimize the loss and optimize the whole accuracy thing, backpropagation is used. Some applications for VAEs would be image generation. They create realistic images from a very good distribution of data. We can do anomaly detection, that is identifying the outliers. And then we can also do data imputations, that is filling in the missing values in data sets. Now, one example I could give would be a variational autoencoder is trained on a handwritten digits. Like we have something called as the MNIST dataset. So after getting trained on it, it can create new digits on its own. It doesn't need all the numbers from 1 to 100. You give a set of some numbers and it can create new numbers for you. So that's what it does. Now, next is GANs, Generative Adversarial Networks. Generative adversarial networks focus on generating highly realistic images. And this happens through a lot of adversarial training. Now, what is that? Adversarial training is where it consists of a generator and a discriminator. Now, this generator creates a data, and the discriminator is going to evaluate it. It is going to see if it is a real image, or if it is actually being seen as a real image, or it is still a fake image. And it's going to throw it back, and it's going to tell that it still seems like a fake one. Can you try to make it a bit more sharper? Now, they can produce sharper images, but they're very harder to train. Why? Because of a lot of data need we want. That like the more data you provide, the better you're getting your accuracy at. And they can also suffer from issues like mode collapse because of the limited diversity. Sometimes the whole like code of yours can collapse if it is not working properly. Now, this training process includes adversarial loss. What is adversarial loss? The generator tries to minimize the discriminator's ability to distinguish between real and fake data. Like ultimately, that's what we want, right? We don't want the discriminator to understand if it's a real one or fake one. So the generator has to try to minimize that thing. So to minimize it, it is going to get better at training, and while it is giving the data, the discriminator would be checking for accuracy. How accurately are your images done? Okay, next is optimization. Both networks, like the generator network and the discriminator network, both of them are trained simultaneously. Where we have these things called as backpropagation, we have something called as gradient descent, and all of these are there to update the parameters or to bring the accuracy down to be very much simpler. Now, some applications of this would be image synthesis, where it is going to create high quality images, very realistic ones. Have you heard about deep fakes? Any sort of deep fakes, anybody?
You can put on chat. Kiran, as you know,
Yeah,
they
you
have to
guys can
mute
put
so
it
they
on
cannot
chat.
speak.
Like, have you
So
ever heard about that? Yeah, yes, I get that. Okay, deepfakes are something where we can actually create realistic images of people from what do we say, from some fake data we have. There might have been a big deepfake controversy on Taylor Swift as well in last year in 2023. She had a whole deepfake video going on, and that was taken down as soon as possible. But then, yeah, we know how fast internet goes on, right? So they can create deepfakes. Of course, it is considered a big, like a sort of a bad thing. But then deepfakes are usually used in creating art, like media platforms and everything. Then we have data augmentation. Now, what is data augmentation? It is generating additional training data. Usually, once we think that our training data doesn't suffice the model, they are going to have to give more training data to it. So that's called as data augmentation. That is, it usually duplifies the data we have. Then we have super resolution. It enhances the resolution of images by putting very finer details. That is where it differs from the variational autoencoders because it gives almost realistic images other than like differed from the autoencoders we are seeing right now. Next up, we can see that this is the architecture of a VAE, that is a variation autoencoder. I'll just brief up. When it goes to the encoder, this thing maps the whole input data to a latent space. Something called as a latent space is where the whole data, the whole input data is represented in a very compressed knowledge. Everything is very completely compressed and it is given in the form of samples. Say Z1, Z2, all of these can be considered as samples. So as soon as the input data is coming in, it is going to go to the encoder and then the whole all the samples from there are going to go to the latent space. Between the latent space, we have something called as mean and variance being shown over here. Both of these are statistical probability distributions. So these are completely necessary whenever you're studying about generative models. So what do these do are, these are going to create the mean and variance between all the samples. Every single sample's mean and variance is created. And all of this is sent to the latent space to better understand it or to distinguish each and every sample, each and every part of the data, if we want to say data. Now, after all of this is done, the latent space is going to create new data points. And then these new data points are again going to go into the decoder. What this decoder is going to do is it's going to take all the data points and it's going to create a new form of data. Like it is going to take all the data points and it is going to represent a completely new data. This new data is then undergoing all the tests and we will be seeing if this new data is actually matching the original data. Simply, that is how a VA or autoencoder works. Now, what is the structure of a GAN or a generative adversarial network? It takes any random noise or like we put it in the form of noises, like any sort of frequency. All the data is put in the form of frequency so that generative network can actually better understand them. And it is going to take that noise as input and it's generating the data that resembles the training data. Similar work, of course, we know that is similar work. But now it uses deep neural networks. As I was saying, we have a lot of deep learning inside this as well. We are going to come into the later part, but now what are what are the kind of deep neural networks used here? That is something called a CNN, that is convolutional neural network. This thing is useful for creating image data and to learn data from the distribution and to create realistic outputs. So they are going to use the CNNs to create the realistic images we want. And after those images are created, it goes into the discriminator network, where it is being compared with the real images we have. And the discriminator network is going to evaluate whether a given data point is real or a given image is real or fake. All of this is something which is generated by the generator itself. So it's going to compare the real images and fake images it has, and it is going to predict it. Actually, like we have seen two different models, right? The VAs and the GANs. There are a lot of things going on. Like there are a lot of exercises going on, experiments going on to combine both of these, both the VA and GANs. And when we do that, it can be combined into a completely hybrid model, that is the VAE GAN model. And this is to push the boundaries of like literally what's possible with generative AI models, because it's going to enable a lot of applications in art, entertainment, medicine, and completely everywhere. Yes, Jeannie, I get that. Okay, I'll try to decrease it. Now, we are able to see what we have seen what is a VAE and what is a GAN, right? VAE is simply nothing but encoding and decoding the data and then trying to create new data. GANs is something where we are going to get a generator to create data and then a discriminator to evaluate it. And depending upon that, we are going to see if it is realistic or fake. Now, what is deep learning? Let us understand the most important part. Deep learning is going to provide you guys the tools which are necessary for the VAE and GANs to be effective. And it also enables them to learn complex data distributions and generate high quality data by not getting too much confused. It is like a very good textbook which is recommended by your lecturer. So until we are VAs, imagine we are VAs, I'm a VAE and you're a GAN. But then, until and unless we are provided the necessary tools like the textbooks or the materials or the resources, can we learn anything effectively? No, right? So, deep learning is that sort of a teacher or the lecturer or the resource we want for us to get better. So, that's what deep learning does in the backend. By definition, deep learning is a subset of machine learning. Now, what is machine learning? It itself is a subset of artificial intelligence. This whole thing involves training large neural networks and make predictions or decisions based on the data. Some key concepts which would be introduced here are neural networks, the most important part of deep learning because it's literally in the name of every sort of deep learning model. Then we have the number of layers. We have something called as input, hidden, and output layers. And then we have something called as the backpropagation and feed-forward neural networking, training, activation functions, etc. All of these, which we are going to see over here in this particular image. What were we talking about? Neural networks. These neural networks are something which are inspired by the human brain. We have neural networks in our head. So, by taking that particular model as an inspiration, we tried creating or discovering this particular model to understand the data, which can be also fed into the computers. So neural network consists of layers, which are also called as interconnected nodes or neurons in our brains. But here, there's something called as layers, and then each single thing is called as a sample. Now, each and every single node is processing the input data which you are providing it. And after processing it in a single line, it is going to get it to the next layer. Simple enough. Now, what are the types of layers in it? We have the input layer, we have the hidden layers, and we have the output layer. Input layer takes in the raw data. Hidden layers are going to perform any sorts of computations and extract whatever features you want, the patterns you want, etc. And then it's going to give it to the output layer. And the output layer, it is going to produce the final prediction, or it is going to do the classification. It's going to identify an object in the image. That's what happens. Now, while all of this is happening, what is the role of backpropagation and feed forwarding? Both of these look like exact opposites of each other, right? The words, they are actually. Backpropagation is a method that is used to calculate and update the weights, and it's going to adjust the weights to minimize the error. While we are doing this, whenever the computation is happening in the hidden layer or between the layer to layer, a lot of junk is created. Like in your computers, whenever you're working, a lot of cache is created, right? In the similar way, a lot of junk or a lot of error is created. To decrease that error and increase the accuracy, what we are going to do is, if you're going to get some 60% of accuracy, we are going to throw back everything into the hidden layers and input layer, and we are going to recompute. That is the backpropagation strategy. And what is a feed-forward neural network? It is a simple flow from an input layer to an output layer. And this usually happens where there are not a lot of amounts of data, because actually it works on very less data whenever we are using a feed-forward neural network. So yeah, now let us understand what are weights. We'll have a small brief through about it. So imagine I've shown you a complete image on how what are the sorts of models, right? Between all these nodes, this is how it looks. All of these are our nodes. we are going to go to the next nodes, and then we are going to create the output. Now, okay, let me just turn on the laser pointer. So yeah, so all of these things are the nodes. These things are like, imagine them as your input layer. And then we have something called as the hidden layer, where computations are happening, and this goes into the output layer. Now, between them, while it is going from one layer to the another, the weights, something called as a particular parameter of it, is being calculated. After calculating this, we can actually call it as the mean and variance, guys, if you want. Some sort of statistical distributions and probability distributions happen at the end. And the weights, all of these weights and the biases which we create are those probability distributions, are the probability calculations we do. After doing all of them, a proper accurate set is sent into the hidden layers. And if you have more than one hidden layer, it is going to compute it between each and every single layer. And then after all of this is done, the accuracy increases completely because we are working on all the weights and all the nodes and all the biases. And then in the output layer, you're going to get somewhere near to 85 to 95% of the accuracy. Usually 85 or like more than 85 is considered a good accuracy. And if you get something called as more than 90, then you have hit the jackpot, because it's never 100% unless and until the data is like literally very small. It contains only 100 rows and columns. It's never that easy to get that much accuracy. Now, there are some applications of deep learning, such as image recognition, where it identifies the objects and peoples. And then we have something called as natural language processing, is going to understand and generate human language, something which the AIs are doing right now. And then we have something called as speech recognition, healthcare. We have some deep learning and autonomous vehicles, robotics, game playing, recommendation systems, virtual assistants, fraud detection, everywhere. Now, deep learning is almost in every particular technical application we see right now, which is automated, of course. Now, some key benefits of this would be automated feature extraction, because there is a difference between something called as machine learning, and there's a difference between deep learning. Deep learning does everything by itself. Machine learning needs a human to be present there. So automatic extraction is something which is a benefit in deep learning. Then we have something called as handling the complex data. Deep learning models are made to handle high amounts of data. High amounts, I mean both high, like a large amount of data, and high dimensional. Now, what are high dimensional? Which have a lot of rows and columns. Imagine one particular data set having only 1,000 rows and 2 columns only. One will be saying your names, the other would be saying your age. That is a very simple data. Even though it's 1,000 rows and columns, it is still a simple data because it has only 2 dimensions. One are your names, the other is your age. Now, higher complex data would include high dimensional data, which contains almost more than 5 to 6 parameters, or more than that as well. We can even work on 20 parameters of a particular thing. Then deep learning has improved accuracy. But then deep learning also needs data requirements. And it also needs some computational resources, GPUs. We lack GPUs in a lot of computers of ours, in a lot of PCs or laptops of ours. Not everybody has a GPU inbuilt inside inside their laptops, right? But deep learning requires that. So we have something called as the Google Collaboratory, which is going to give us those computational resources, so that we don't have to find an external GPU to be connected. So that's how it is going to help in deep learning. And we have interpretability. Deep learning models usually see something called as black boxes, which actually makes it difficult to understand the situations or the decisions they make. But yeah, those are the benefits and challenges I wanted to just iterate. And these are some of the more applications of deep learning. Now, some popular architectures of deep learning would go to convolutional neural networks, which we were just talking about. These things are designed to process structured grid data like images. You're able to see the image over here, right? All of these, imagine them as grids. And since convolutional neural network works on image creation, imagine all of these as images, some data set of images which you're providing. It is going to read a set of images at a single amount of time. It's going to take whatever it can, and it's going to send it to the next layer. After sending it, it's going to create another group again. It's going to understand a difference and similarities between that, and it's going to send it to the other layer. That is how a convolutional neural network works. Particularly, they have a lot of convolutional layers between them, and they are to automatically detect the patterns and features in those images, like the textures or edges or the colors, etc. All of these is done. Now, after doing that, it's what it does is it enables images related tasks only. And due to this, it is going to enable advancements in areas like medical imaging and autonomous driving and quality control as well. Some more applications we can see are in the retail and e-commerce section, where we can see product recommendations and image research. We can take the example of Amazon's image search. Like recently, we got a like update in the Amazon site where we can search via images. So that's what is happening because the CNNs are working in the backend. In the sports and analytics field, we can see a player tracking in soccer. So player tracking and performance analysis keeps happening, right? In cricket or soccer or anywhere. All of these are monitored by CNNs. Any sorts of fouls or goals or offside they put, all of those. Next is healthcare. Some one prominent thing that CNNs are doing is the skin cancer detection. That is like literally very much prominent these days. And Stanford University's dermatology AI is actually researching on these. How to use CNNs to develop a model that can identify skin cancer just from the images of any sort of skin lesions we have. Then we have manufacturing. We have quality control and defect detection. All of these are some case studies or examples and real life applications CNNs are used for. Next, let us go to RNNs. All the images depicting on the right side are very simpler models to make you understand better if you are completely new to this sort of topic. So yeah. Next up is the recurrent neural networks. Recurrent neural networks are completely designed for sequential data. For example, we have something which is time prominent. So RNNs are only designed for that. They are designed for time series. Now, what they do is they use loops within the network and they use it to maintain information about the previous inputs, which can also make them effective for tasks like language modeling and speech recognition, etc. So they are going to put understand the whole network inside their input itself. They're going to loop within their own network and understand what the data is again and again iteratively. This is going to help the RNNs to give better output since it is being trained on the similar data or the same data again and again. And some applications of this would involve in the financial sector, we can call something called as a fraud detection. A lot of credit card fraud detections are happening by using the deep learning networks. The customer service, the chatbots and virtual assistants all work on deep learning and RNNs play a big part in it. Education, personalized education and adaptive learning platforms, all of these also require deep learning. Everything in the backend, even though we see that we can create a website without coding, but in the backend, we see that there is a lot of coding taking place. Users are getting a better environment to push all of them in a single space without actually touching the code at all. Energy. Now, there is something called as the smart grid management, where whole load forecasting and energy management is being taken place, and RNNs help in that as well. So all in all, RNNs are completely in for the sequential data and time series data sets. And usually RNNs and CNNs are the strengths of the neural networks. They help in businesses and researchers, and both of them can actually continue to push the boundaries of what is possible in deep learning if they are also integrated and synergized. If they do, they can create smarter and more efficient and more responsive systems across a wide range of fields. And I guess it is already in effect. It's already happening. A lot of artificial intelligence, even though it's a tiny bit of text image creations or text creations, to a very large artificial intelligence actually becoming a Jarvis for you. We can see deep learning and machine learning and all of this going in the backend. And somewhere RNNs and CNNs play a major part in that. Like, who wouldn't want a Jarvis for themselves, right? I would actually love to create one and install one on my laptop. That would be my next project. Now, while we have understood what is generative models and what is deep learning, right? Let us understand how deep learning is enabling the generative models, how it is actually giving the power to generative models. we have something, we have a lot of situations over here. Deep learning is actually helping it in many more ways. First one is a neural network. Generative models rely on neural networks to learn and represent complex data distributions. And deep learning frameworks like TensorFlow and PyTorch provide the necessary tools to build and train these networks. We have TensorFlow and PyTorch are a part of Python libraries, and both of these are completely very useful in creating any sort of deep learning algorithm we want. I'll be showing you a simple example later. Next, we have something called as the training techniques. We have like deep learning usually introduces to techniques like backpropagation and gradient descent, and something called as the regularization techniques and advancements in network architectures. All of these are essential for training the large and complex neural networks which are used in the generative models. And regularization technique also helps in improving the stability and performance of these generative models. So that's how they work. Once, like backpropagation and gradient descent, you can see the images on the right side. Like you can understand and get a gist of how actually they work. Gradient descent is going to help you get to the near accurate point, or we call as the global variable. It is going to help us to get to the most accurate point by understanding the differences between each and every rate or each and every point of data. We have something called as underfitting, optimal, and overfitting of the data as well. These things are going to help us first understand the data, and the regularization technique which we are talking about is going to help us to either make the underfitted data into an optimal data or an overfitted data into an optimal one. How? We are going to decrease or increase the complexity. We are going to add models or completely delete some models. So that's how training techniques help. The ultimate goal of the training techniques is to bring it to the most accurate point. Next, we have something called as the architectures, where CNNs and RNNs come into play. Convolutional neural networks are used in generative models like GANs. You can see a complete structure over here. It is very complex, of course. But then a generator, we have seen how a generator works, right? It takes the input and it creates a lot of new images, and then it throws it into the discriminator. So while that is happening, generator is actually going to understand and separately go through every single part of the image data which we have provided. This is going to help, this is going to be informed by the application of convolutional layers. They are used in GAN for processing the data, and also it enables the creation of realistic images. Now, how are RNNs working? There is something called as the long short-term memory network, another sort of deep learning model itself, but it works in a different way. RNNs, we have seen that they are continuously iterating between themselves and understanding it, right? Long short-term memory, what it does is when you're going from one layer to the other layer, whatever is unnecessary, it is going to keep it for only a single term. It's going to keep it for only a single point of time until and unless all the data over here is going to this particular thing. It's not going to come back. It's not going to save the data or save any unnecessary thing or any sort of unnecessary data with itself. It's going to delete that. Whatever is necessary only goes forward. So RNNs and LSTMs are going to work in a way where it is used in sequence generation tasks, such as text and music generation. And all of this is done by modeling some dependencies in the data. Now we are just going to work on a lot of input data and a lot of hidden layers and all that. And then LSTMs and RNNs are going to work like that. Now, before, we have seen all the situations here, right? We have seen the architectures, we have seen the training types. We have also seen how the neural networks and how they're actually working. Now let us understand a small process. This process is going to help us understand how deep learning enables the generative models. And it's completely 6 steps of things which are involved. First, it involves detailing the processes and the steps that leverage deep learning principles to build and train these models. Let us go through this structured inflow or the workflow. And we can also focus on VAEs and generative adversarial networks also. Now, deep learning provides the computational power and techniques. We already know that. Neural networks and backpropagation, all of this is the power or the backbone we need. This is going to enable the generative models like autoencoders or adversarial networks to create and learn the complex data and then generate new ones. For the particular thing, for that particular process to happen, first step is the data preparation. We are going to collect the data, whatever large data sets or like which are relevant to the task. If you want image data, if you want text data, if you want audio data, you're going to collect that large data set. Then you're going to pre-process it. You're going to normalize the data. You're going to bring it, like we have example, we have some accuracy we want, like we are hypothesizing the model. We want the accuracy from 0 to 1 itself. So we are going to pre-process the data by normalizing it. And whatever data we have, we're going to split it to something called as the training data and the validation set or the testing data set. Next up is the model architecture design, where we are going to choose the model type. Is it a VAE, that is an autoencoder, or a generative adversarial network? And then if it is a decoder or a discriminator, like that. After we are going to take all of this, we are going to put all the convolution neural networks we want, all the CNNs we want. Then we are going to go to the training setup. Training setup contains two parts. One is defining the loss functions and choosing the optimizers. We have read about the loss functions, right? It's all about decreasing it to the accuracy. So we are going to see how much loss function is happening, and we are going to choose the amount, like a proper optimizer to bring it to accurate level. So all of this is happening in the training setup. Next step is the model training. After you're actually done choosing your optimization and all that, you're going to start the training, and you're going to use these things called as the forward pass and the backward pass, similar to feed forward networking and back propagation. And then you're going to compute the losses, you're going to update the weights, and you're going to iterate, like how we have seen in the CNNs and the neural networks. If it is something which we don't want, we're going to throw back into the model and we are going to ask it to train it again. Next, we can see model evaluation and tuning. After the whole thing is done, after the whole model training is done, the model evaluation and tuning happens, wherein we see the validation. The validation data set comes into picture. They are going to give it to the computer and say, you have worked on the training data till now. I want you to do the same thing on the validation data set and give me something which I need. Give me a proper, output which I actually am desiring. If the validation data is working, if the whole deep learning model which we've just created is actually working, the validation is going to give you very high accuracies. It can be 90%, it can be 85, it can be 93, anything. After all this is happening, if it is less than 85, what are you going to do? You're going to see that it is not having that much accuracy, and you're going to start tuning it. After you start tuning it, like fine tuning the model, right? After you start, whenever you are actually creating a music and you see that this particular music is not actually working properly, you're going to tune it. You're going to see what sort of chords and all are differing in a guitar, for example. Similarly, we are going to tune the model again. We are going to give all the weights back, and then it's what it does is, after it's completed its training and all that, training and testing, it's going to generate the samples which we need. After it's generating the samples, what we are going to do is we are going to see if the samples generated are actually like similar to what the original data we have given. If they are, voila, you're done with your work and you're like succeeded. You have succeeded in creating a deep generative model. And if it not, you have to go back into the model training again. You have to go back into the training setup again. You have to see if the model architecture design differs. So all of these steps need to iterate if the generated samples are not actually accurate. If they are accurate, you have to save the model. You can deploy the model into a website, and then you can keep monitoring and updating the models as you wish. Now, this is a very simple model of what I wanted to say. Let me show you a simple, what do we say? 1 sec. Yeah. I hope the Google Colab is visible. Yeah. So this is a simple model which we created once. And I can, as you can see, yeah. So this first thing is importing the TensorFlow, and we have seen, right? TensorFlow and PyTorch are two different deep learning libraries of Python. So these things are where we start data pre-processing or data preparations. Here we have given the MNIST data to be loaded. And of course, I have used a very low amount of image data, so the desirable output hasn't come yet. But then if I start giving it the actual measurements and start giving it a very large amount of data set, it's going to give me accurate results. For now, my accuracy would be around some 40 to 50% if I have to show you. So now the data preparation has happened. Next, we are going to do the sampling function and latent space. All of these are defining the loss functions and training. After all of this is done, we are going to give the latent inputs, and then we are going to put our auto encode a model. We are going to give all the data requirements for the model. We are going to train the images. Epochs here are the number of iterations you want the batch to be trained on. So what happens is the MNIST data is very big one, right? There is it's a very big data set. What I'm going to do here is the batch size over here, 128, represents the number of images I want to, or I want the data set, or I want this particular Google Collaboratory to take. It's going to take the first batch of 128 and it's going to run 10 iterations over it to understand the data. Similarly, how many ever batches it gets of 128 set each, it's going to run 10 epochs or 10 iterations over it time to time. And depending upon the loss function over here we can decrease the loss function or increase the loss function by actually using some tuning parameters, which I haven't used, which resulted in these sorts of images. They are not completely blank because we can see that there is something in the backend. But then since I have actually not defined how to fine tune the losses and everything, it's going to give me completely blank images. So that's the difference. I can show you another deep learning model which was created yesterday. Here you can see the data preparation happens where I'm giving my training and testing image, that is the validation image, and I'm going to give the batch size here itself. Then we create a proper generator model and a discriminator model, and we also check all the loss functions, and we are going to put all the functions we need over here. And then we're asking it to generate and save the images. What it is going to do is it's going to give me a big set of images. As you can see the scroller on the right side, it has those many images over here. It's going to go from completely blurred images to completely a bit more fine-tuned images, right? You can see the difference between that and this. I hope the screen is actually visible. You're able to see it. Yeah. So as you can see the difference, that's a completely blurred up image. And this is something, it's showing us a pattern, isn't it? So that is the difference between a particularly trained model and a completely untrained model, which I have shown you before. Now, what I did is after it generated to some sort of thousands images, I asked it to only take out the last 15 or 16 images which I need to exactly understand what image it is actually creating me. Because I haven't given it an image to create. I just asked it to randomly do something for me. And it has created some random images containing a particular pattern. Now, what I did is I'm going to use the same model to actually ask it to create a prompt for me. This is a very simple prompt where I've taken, we know ChatGPT, right? ChatGPT can also be used in our code by using the GPT-2 tokenizer. And after we use it, we are going to ask it in a similar way where we ask ChatGPT. We are only going to give it the prompt we need, and we are asking the generator to generate a particular amount of text. And it does create it for us. But then all of this is not highly trained at all. Why? Because it contains large amount of data. It needs a lot of amounts of data. And those amounts of data need a lot of computational resources as well. As I said, Google Collaboratory is actually helpful in doing this. It's actually helpful in giving us all the GPU related computations we need. But ultimately, even Google Colab has its own limitations. We need to go through a lot of other computations like the VS Code, if you have heard, and then we have something called as Jupyter Notebook. Those might help, but then it also depends upon your laptop. To be honest, this whole image creation took me almost 1 hour to be created. So it needs that much of computational resources and time. Usually deep learning is, that is the reason deep learning is not recommended in any sorts of laptops. Mine might not be supporting this. That is the reason it took 1 hour or so. If you have an inbuilt GPU in your own laptop, and if you can run this whole code over there, probably it might take you only 5 minutes. Who knows? As you can see in this particular code which I showed you, the epoch, every single epochs or the iterated things, seconds or the computational time is also being shown. Per step is going to take 367 milliseconds. If you have a proper GPU, it might take up to some 5 milliseconds, and that is going to decrease a lot of time for you, right? Like 367 and 5 are nowhere to be compared. So that is how it differs from model to model, and that's how deep learning is completely helping us in understanding or in creating generative models, and it's also enabling them to give us a very good accuracy in the images. So that is all I had to deliver today. I'm open for questions, guys.
Thank you, Kiran. There's a lot of great content. I know it's a very technical topic and a lot of things to be covered and covered in a short period of time. So thank you for doing that. Team, I put feel free to put questions. I don't see any questions so far in the chat. We'll open up for Q&A in a bit if somebody has verbally, but feel free to add questions. While we wait for questions, I'm going to share a quick resources. So I'm just going to share my screen. I put a bunch of links on the chat, and what they are free resources and some other next steps possibly. So we have several meetup groups you can join based on your interest of what you're doing. There are 5-6 different meetup groups, and I've shared the link so that be part of that particular interest, whether cloud, whether AI, whether jobs, whatever that may be. Join those particular meetup groups. All the recordings from the past we usually post on our YouTube channel. So you'll see some past ones posted. This is also going to be posted in a few days. So you'll get recording. That link is also available. We also offer, we mostly do corporate trainings, but we do offer public trainings. And this is a set of public trainings, upcoming ones, where you have live training, whether 3 hours, 6 hours, several days of training, which can happen live on Zoom. We also have several on-demand trainings. Several of them are free, some are paid. So you can access that. I would highly recommend if people are interested in ChatGPT to look into this one. I think it's very phenomenally done, one of my top instructors, and it gives you a whole new lens into ChatGPT. You may think, ChatGPT, you'll be surprised, or you can definitely get some golden nuggets from this. So try that out if you please do and wish. These are some of the upcoming webinars. So we have a cloud computing one coming up soon, and then there is Microsoft Azure, both of them cloud, one on GCP, Google Cloud, and then on Microsoft Azure. So those are some of the next possible things which are coming up. But I want to thank Kiran for the wonderful session. Very well covered, quite a lot of content. I know there is a lot to be covered in a very small period of time. So I appreciate you going through it. And with the content and everything. So I see a lot of positive comments coming in the chat, but no questions. So feel free to put any questions you all have. I'm going to stop recording. Thank you, everyone.